Ladies and gentlemen, do you agree if I say that the human development is actually driven by the development of new materials? Can be related with the period of human history. Let us travel back to the beginning of Stone Age over the million years ago where the human only accessed natural materials such as stone and wood. But later, they start to develop materials that have superior properties compared to the stone by adding the alloying elements. For example, a copper was added into the tin in small scale to produce bronze, followed by the production of steel, which primarily consists of iron and carbon with high strength. From time to time, the scientists discovered the relationship between the structural elements and properties. One simple example is nickel superalloys, with excellent heat resistance and been used in jet engine for the military purpose. This great development became driving factor for the Industrial Revolution. Let us thanks to alloy, a mixture of metal with one or two principal elements, where the minor fraction of other elements are added for the property enhancement. In fact, we actually have identified almost all the elements in the periodic table and developed numbers of conventional alloy systems from that. Perma alloys, aluminum alloys, also high-speed steels. However, the properties of these different family alloys materials are very limited. Even if we add further alloying elements, it will lead to the multi-phase of alloys with complex microstructure. So, what is the effective strategy for us to go beyond and become more advanced to meet the needs of our modern society application? What happens if we design alloy not from one or two base elements but from the multiple elements together? This is what the idea of high entropy comes from. Assalamualaikum and hi everyone. Here I am Nur Alisha, a final semester student of Material Engineering from IIUM, will sharing a lecture entitled as Performance Evaluation of High Entropy Alloy as Advanced Materials. This is the outlines for my lecture today. Now, let us explore together what does it mean by high entropy alloy. According to Ye's theory, high entropy alloy is a solid solution alloy system with 5 to 13 metallic elements, and the range of element concentration is starting from 5 to 35%. It is also known as equiatomic, multi-principal, or multi-component alloys. What does this term mean? Simply said that this type of new alloy is developed by mixing many metal elements together in equal or near equal proportion. It is different with the conventional metallurgy that require only small amount of elements to modify the properties of the base materials. The concept of high entropy alloy are studied based on the thermodynamics, Gibbs energy, and mixing entropy. This figure shows that the minimum limits of number elements to form a solid solution phase must be 5. This is because at this point, the mixing entropy is sufficiently high enough to compensate the mixing entropy in the alloy system. In the entropy viewpoint, high entropy alloy is considered as extension from low and medium entropy alloys, means that it is highly disordered with lower energy. To illustrate my point, let's have a cup of solid ice and liquid water. Which one do you think has the higher entropy? The answer is liquid because the arrangement of the atoms are more disordered in the random arrangement compared to the particles in ice cube that are tightly packed together. So, in order for them to hold their bond together and maintain its structure as ice, it must require high energy, right? Similar concept to the high entropy alloy. The more number of elements that we are added into the system, the higher the randomness, so the higher the entropy will be. What about the solid solution? The formation of a solid solution or solid solubility in high entropy alloys are governed by the Hume-Rothery rules. So it can be expressed by two parameters, different atomic size and omega. As you can see, the solid solution phase of high entropy alloy are distributed in this orange zone in the large omega and small atomic different size. This is because the low strain energy from the lattice distortion and the effect of mixing entropy cause the high entropy alloys to be stable enough to form a solid solution. The another point is the type of solid solution can also be predicted by calculating the valence electron concentration. Next, moving on to the four core effects. First, high entropy alloy, which mainly refer to its main characteristic, which exhibit formation of simple solid crystal structure, such as PCC, FCC, and HCP. And then the sluggish diffusion that discuss different diffusion rate for each element in high entropy alloy. The third one is the lattice distortion that strengthens the solid solution formation. This is because the highest lattice strain will impede this dislocation in its system. The fourth one is the cocktail effect, which is considered as the result of composite effect on the atomic properties. It means that the different composition elements will promote the different microstructure, phase, and properties. Okay. For example, this figure shows the variation of crystal structure from FCC, missing FCC, and BCC, with the increasing composition of aluminium. So here we can see the maximum hardness is at 0.9. Why it is not at 15 or 20%? Because if we think by logic, the higher the percentage of aluminium, the harder the object will be, right? But unfortunately, this case is different because of size interface area between FCC and BCC phase are actually increased. This can also be related with each microstructure, which shows the exquisite dendritic grains with the finest size of the spinodal and the interconnect structure. The relationship is the smaller the width, the bigger the interface area, so the lesser the dislocation of mini-free path that will increase the hardness. Now, I want to introduce to you the first high entropy alloy which developed in 2014. It is known as counter alloy. For your information, this counter alloy has been nominated to be the toughest material with a tensile strength higher than 1 gigapascal. Because of its superior mechanical properties, the trend study on high entropy alloys start to increase, especially in improve the mechanical properties in various applications such as the cutting tools, corrosion protection, nuclear reactor, and also engine turbines. And now, the current trend is more focused into the development of high entropy alloy as catalysts. Um, Now, the study shows that they are able to generate various numbers of active site for the catalysis reaction. So, this is the catalysis mechanism for the high entropy alloy, which is similar to the metal and alloy. Generally, we are always familiar that the absorption happen in 3 steps. But to make it clear, I will describe the heterogeneous catalysis into 7 steps. It starts with the transportation of a reactant to the solid catalyst surface, and then it went to the pores, followed by the absorption of the active site of the catalyst particles. And once it reaches the active site, the reaction proceeds by rearrange the electron and form the adsorbate product. Then this desorption product will release from the active site to the pores and going out to the solid surface. According to the previous research, these are the factors that influence the catalytic performance. Okay, let's see this formula. The higher the specific surface area, the higher the reaction rate will be. So to increase the surface area, high entropy alloy must be synthesized by reduce its particle size into the nanoscale. The simplest method that we can do is by mechanical alloying. Mechanical alloying is defined as a solid-state powder process where the powder particles are mined and exposed to the high energetic impact. So this is the illustration on how the synthesis process works. The opposite rotation directional between the bowl and the disc create the centrifugal force. So the friction between the milling ball and the powder mixture cause the metal powder to be flattened and cold welded under the high energy collision. As a result, we will get a homogeneous mixture of high entropy alloys in the nanoscale size. So to get a better view on this, let's take a look on this micrograph. Initially, all the different elemental powder shows different morphology such as spherical, irregular, and flake shape. But after undergo the milling at 3 different times, we can see that the size particles become smaller and homogeneous. This example doesn't mean that the higher the milling time, the smaller the particle size will be for every single high entropy alloy system. What does it mean that what I mean is because the process parameters such as pore to powder ratio, milling speed, time, and process control agent are not entirely independent with one another. Instead, they are vary by type of elements, composition, and type of mill. This is the important point that we must understand when dealing with the mechanical alloying. This method must be done in the specific condition to avoid any contamination and oxidation of the powder. Okay, for example, The particle size of these aquaatomic high entropy alloys was increased and become non-homogeneous even after 20 and 50 hours of milling. This case can be related to the wrong usage of PCA and insufficient speed that results to the agglomeration. So, in order for us to obtain the homogeneous mixture, we must understand the relationship of the elements with the parameters. And next, this is the application of high entropy as catalyst. In the degradation of azodite, the purpose of high entropy alloy to be a catalyst is mainly aligned with the six sustainable development goal that specifically focus on preserve the sustainability of water in the textile industry, specifically in the textile industry. This is because it has been considered as the second most polluting industry due to the improper disposal of wastewater that contain high toxic chemicals, especially azotides. Even though that we know the azotides give high intensity color to the fabric that we use every day, they are actually highly toxic to the human being and aquatic life. So let's have a quick discussion about the performance of high entropy alloys in this application. Okay, this is the result of after milling process. Um, this SRT pattern shows that there are three different high entropy alloy systems generate a simple solid solution phase. So that also has exhibit uniform distribution with high specific surface area. Next, in this degradation curve, we can see that all three curves here demonstrate excellent performance. They took shorter times to degrade the azodite. Among of them have different reactivity of metals that influence their degradation efficiency, where there are decrease in order chromium, cobalt, and nickel. So that's why the degradation rate shows by the chromium is the shortest with only 11 minutes. Okay. So surprisingly, if we compare it to the widely commercial use of alloy, the degradation efficiency is 90 times greater and more than 100 times greater than commercial zero-valent iron powders. So one of the factors that contribute to this excellent performance are milling process, which can be related with what we have discussed before, where the process induces the plastic formation and increase the lattice distortion energy. So the powders are in fact, these powders are in metastable state, which can be achieved by other two conventional alloys. Okay, overall, the high entropy alloys that we are discussed developed based on the multi-component alloy system shows really superior properties either in the mechanical and chemical reaction. So its performance as catalyst can be generally understood well through the four core effects and synthesis process itself, which is mechanical alloying and other process. So actually the study on the performance of high entropy alloy as catalyst is still considered as new development, and there are still more open questions that we need to be discussed together. But until this point, I feel that it has very great performance and properties, and it's really interesting because from what from what we just discussed together, I can conclude that the high entropy effect, I can conclude that the high entropy will give excellent opportunity for us to expand the diversity of materials. So I think that's all from me, and I hope all of you will really understand and enjoy my lecture. Thank you. Assalamualaikum.